Hello, and welcome to the OpenSystems Media eCast titled FPGA as a Game Changer for Military Communications. My name is John McHale, Group Editorial Director with Military Embedded Systems and moderator for today's event. Our speakers today are Noah Donaldson, Vice President of Product Development for Annapolis Microsystems, and Rodger Hosking, Vice President and co-founder of Pentec. Noah Donaldson has earned a BS in Physics from Carnegie Mellon University in 1995. He started at Annapolis as an intern. Eventually worked on high-performance FPGA boards and mezzanine cards, developing some of the first greater than 1.0 GSPS multi-channel synchronous digital receivers. Today, Noah oversees all product development and business development for Annapolis. Rodger Hosking is responsible for new product definition, technology development, and strategic alliances at Pentec. With more than 30 years in the electronics industry, he has authored hundreds of articles about software radio and digital signal processing. Prior to his current position, he served as engineering manager for WaveTech Rockland and holds patents in frequency synthesis and spectrum analysis techniques. He also holds a BS degree in physics from Allegheny College in Pennsylvania and a BSEE and MSEE degrees from Columbia University in New York. And now for some short housekeeping announcements. Please note that this and all OpenSystems Media eCast are copyrighted and may not be recorded or used in any way without the express written consent of OpenSystems Media. The eCast will consume about 35 to 40 minutes, leaving the remaining time for the question and answer session. I also want to point out some important buttons on your screen. First, please take note of the Enlarge Slides button. By clicking on this button, you'll be able to view the slides in full screen mode. You can also use the Download Slide button to view the slides as a PDF if you want to see them larger. The second important button is the Forward to a Friend button, which enables you to email a friend to register for this event. Third button on your console window allows you to enter questions in real time. We'll do our best to address these questions during the closing Q&A session. If you have a question intended for a specific speaker, please note so at the beginning of your question. Otherwise, I'll hand it out to the speakers equally. If you have a question pertaining to the eCast operation itself, one of our technicians will respond back to you during the eCast. Please note that as much as we like to, we may not get to all of your questions today. In that case, someone may get back to you after the eCast with more information. This eCast will be archived online and be available for 1 year. There will also be an MP3 version of the event available. And now I'm pleased to turn over to our first speaker, Noah Donaldson. Noah, take it away.
Well, thank you very much, John, and I'd like to thank all of our audience members also for taking the time to join us today on this webcast. We thought that, when speaking about FPGAs as a game changer for military communications, first it would be good to just do a high-level overview of the differences between different types of processors in a DoD typical program. So we came up with this little chart to compare CPUs, GPUs, FPGAs, and ASICs across a range of different categories that are important to DoD applications. So we're going to talk about a mil comms environment here. And first is NRE. Little to no NRE is, of course, what's desired from most military programs. That may not be achievable, but that's a goal. In that respect, the FPGA stacks up quite well. The ASIC, of course, has quite a lot of NRE typically involved, and CPUs may have the lowest NRE, but an FPGA and a GPU stack up pretty well depending on your development environment, which I'll go into a little bit later. For time to market, of course, shorter deliveries so that we can deliver these systems to the warfighter as soon as possible is critical. And in that respect, again, the FPGA stacks up very well compared to an ASIC, and depending on your development environment, is pretty comparable to a GPU as well. As far as power is concerned, of course, there are always swap restrictions, and as we move to more unmanned vehicles and smaller platforms, that becomes even more difficult to achieve. And there, an ASIC is sometimes the best technology to use, but FPGAs being flexible and tailored to the application is also very good, typically much better than a CPU or a GPU. As far as technical suitability, how flexible is the processor to do what's required of the application and do it in a high-performance way. The FPGA may not be quite as good as the custom-designed ASIC, but is typically much better than a CPU or GPU, especially for very high bandwidth or for interfacing to an ADC or D to A converter. As foreign military sales become more important and as more of these systems get fielded into hostile environments, security becomes critical in protecting the IP on these platforms. And in that respect, an FPGA and some of the security features available there can actually be one of the best solutions for that in that category. As far as upgradability, these programs have long lifetimes, so inevitably some sort of upgrade is required. And there, the FPGA is very well suited. It being a reprogrammable device, you can change it obviously very easily. You can purchase those systems with plenty of horsepower available for the future for putting more processing into them. And as far as product lifetime, 20-plus years of life required out of these programs usually. The FPGA and the ASIC stack up very well and have long lifetimes, whereas the CPU and the GPU typically are for a more commercial, industrial environment and often aren't available for as long as the other processing types. Now to go into a case study where we had a program that we were working on for a software-defined radio system. It's for an airborne communications. The system itself is located in a pod on the exterior of an aircraft. And it had some swap considerations that were very important. So we came up with our COTS FPGA processing system. So that consists of our Wild 40 3U chassis. So there's a chassis designed to hold the FPGA cards and SBC and power supply. It holds conduction-cooled versions of these cards, as well as ADCs and DACs. And the chassis itself is air-cooled with a large fan. Here you can see some simulations of the chassis. It has to endure a very high ambient air temperature while, of course, keeping all of the components inside cool enough. And we found that the simulations were shown to be very accurate compared to the real-life environmental qual that was performed later. The top picture shows a cutaway view of the chassis where there are 4 ultra-scale FPGA 3U conduction-cooled modules, 1 conduction-cooled SBC, and 1 conduction-cooled VITA62 power supply. You can see an example VITA66 and VITA67 compatible backplane used for that can be used for military communications. This particular backplane is a 14-slot backplane. Has 2 power supply slots, 1 data switch slot, which it has PCI Express switch, 1 radial clock slot, which is used to synchronize multiple ADCs and DACs, which I'll go into later, and 1 control switch slot, which has an Ethernet switch, as well as 4 payload slots where FPGA card and other types of processing cards can plug in. This backplane, like all of our backplanes, is designed to support at least PCIe Gen 3, as well as 40 gigabit Ethernet, which has 10 gigabit signaling rates. The processing boards in this system are our WildStar Ultra KVP boards. So they have an ultra-scale FPGA processor, either a Kintex or a Vertex type, or even an ultra-scale plus type is pin compatible. We also have 6U versions of these cards, and we also have coming out this year, or in 2017, we'll have Stratix 10 versions of these cards. There's DDR4 DRAM for high bandwidth connectivity, high bandwidth buffering, and also wild FMC Plus I/O site for ADC and D2A connectivity. The block diagram for this card is shown here. The red block on the top is the I/O processing element. Basically, that's the large FPGA that's used for the majority of the signal processing in the system. This is an ultra-scale or an ultra-scale plus processor, either Kintex or Vertex. The two blue blocks are the DDR4 DRAM ports. There are two 80-bit ports. Each of them can be either 5 or 10 gigabytes. The I/O to the backplane is shown as there are two PCI Express 4X ports, and there are 3 4X agnostic lines, which are shown in blue, and those could be running some custom low overhead protocol or an Ethernet protocol where we provide 10 gigabit as well as 40 gigabit Ethernet protocols, both in R and KR variants, where KR includes FEC and auto negotiation, and those types of cores are included with the hardware. The teal box is showing Zinc 7 SoC FPGA. So it's an FPGA with an integrated dual ARM CPU. We deliver this product with Linux running on that dual ARM CPU, and it's what we call the host processing element, the HPE. So we have a suite of firmware and software running on that SoC that hosts the entire card. So this card could be simply plugged into power and no other backplane connectivity, and it could come up and run its own application standalone if that's what's desired. And then in the top left, you can see the I/O site. So this is our Wild FMC Plus I/O site. I'll go into what Wild FMC Plus is in a little bit more detail on the following slides, but here you can see what's critical is that there's a blue connection and a red connection to the FPGA, which have 32 high-speed serial and 100 LVDS, which are high bandwidths than are higher width buses than are available on a standard FMC Plus. And also there are 2 yellow boxes. That refers to the fact that Wild FMC Plus is stackable, so you can stack 2 mezzanine cards into the same I/O site. One of the mezzanine cards used in this system is our 16-channel WildStar mezzanine card. It's a very high-density solution. That means 16 channels and a single mezzanine site. That is what enabled us to achieve the low swap for this system. Most other cards were in the 4 or 8-channel range. This density helped us achieve a much smaller and lower power system. This particular card is a 125 megasample per second, 16-bit ADCs, and it's available. It can be synchronized. You can synchronize multiple cards across the system if there are multiple cards that's required. We also have other mezzanine cards, dozens of them, up to the 5+ gigasample per second range. One of the most important features of this card for this particular program was the crosstalk isolation. There's a requirement of at least 80 dB of isolation between all of these 16 channels. Fitting that into to this small size, high density was particularly challenging. But we were able to achieve it. So you can see the crosstalk isolation shown here as a channel-to-channel table. Storage is also can be very useful to a military communication system. This is showing our single slot 3U SSD storage solution. It's available in an 8 terabyte depth today and almost 17 terabytes coming soon. It has PCIe interfaces to connect up to SBCs or FPGA cards. It has a very high bandwidth, 6.4 gigabytes per second, so you can have very high bandwidth ADCs and store raw data to the storage. And it also has a canister carrier configuration so that you don't have to unplug the entire card from the backplane when it fills up and when you need to put blank storage in. Instead, you can just unplug the canister, which has 10,000 insertion cycles on its connector, so that you can go through many mins without running out of insertion cycles. And that canister and the carrier are hot swappable, as are all of our OpenVPX boards, which can be very beneficial in certain programs in the deployed environment, but is especially beneficial also in the development phase, because that means that multiple developers can develop on multiple boards in one system, even if they have to be powering off and on those boards. They can do that without powering down the whole system and turning off power for all the other developers at the same time. Our Wild FMC Plus mezzanine form factor. So we had to achieve some very high bandwidths in order to achieve the high densities that were required from our customers. So we looked at FMC and FMC Plus form factors and determined that in our new line of products, our UltraScale and X10 products, they weren't going to be a high enough bandwidth. But we wanted our customers to be able to plug an FMC or an FMC Plus into our boards if required. So we came up with what we call the Wild FMC Plus form factor, where it has the same mechanical and electrical specification as FMC Plus, but there's an extra connector that allows us to achieve the 32 instead of 24 high-speed serial and 100 instead of 80 LVDS. And I mentioned earlier, these are also stackable, so you can achieve twice the density per FPGA carrier card. Another couple problems I'd like to point out is had programs that have required synchronization of thousands of ADC channels at the 2+ gigasample per second rate. So very high density mezzanine cards weren't feasible, but instead we elected to, when we sort of had a hand in coming up with a radio clocking solution, which involves repurposing some lines on the backplane to enable synchronization of many mezzanine cards, many ADC and DAC channels with minimal cabling on the front panel. Another problem is deployment and maintainability of systems in the field. So we've worked on improving this for upcoming systems, and blind mate RF and optical connections is critical to allowing that to happen. So as many connections as you can move onto the back plane as blind mate as possible always makes these systems easier to deploy and keep maintained in the field. Radio clocking also helps as it moves more connections to the back plane, as does hot swappability and security features to allow these products to go into hostile environments. And lastly, how do you program these FPGA applications? As I outlined on the very first chart, I claim that the FPGA could have as low an NRE and as quick a time to market as GPUs. That may not be achievable in a purely HDL development environment, which is why we came up with this development environment, which has been out since the year 2000, and we've been upgrading it constantly since then. This is an environment where you can either work in the VHDL or Verilog world, or you can work in this graphical environment. And what you get are all of the Annapolis board support cores, so that's ADC NAC cores, PCI Express, 40 gigabit Ethernet, things like that, as well as the algorithmic and data flow cores. You can integrate them all together into one environment in order to design the particular application that you want for your FPGA board. So whether that be some sort of down converter or something else, you can build that up out of these blocks custom. And the sort of development flow of using this system, Open Project Builder, is that you put together on the top left board support packages, which we supply to you with the hardware, together with what I call the user space cores, so the signal processing cores, math cores, data flow cores, things like that. Those cores can either be HDL that you import, or you can use the cores that we already include, that we give you for FFTs and for filters and things like that. You put them together into the in the environment, and then you can either take the fast path, go straight down, and create your image for the FPGA and develop your host code in either C or Java, or you can take an exit ramp that allows you to output HDL from the design, so that you can continue to develop and simulate in an HDL environment. So that gives you an overview of sort of how Annapolis sees tackling some of the military communications type of program challenges, and what we're trying to provide in order to make that a little easier for our customers to do that integration and support. Back to you, John.
Thanks, Noah. And just a reminder to the audience, keep your questions coming in, because after our next speaker is done, we will start the Q&A. And speaking of our next speaker, I would like to introduce Rodger Hosking. Rodger, take it away.
Thanks a lot, John, and thanks everybody in the audience for joining us today. As you may know, Pentech has been in the business of providing high-performance data acquisition, data converters, coupled tightly to DSP resources for nearly our entire 30-year career. So today we're going to be focusing a little bit about on how FPGAs are a great asset when you're trying to solve communication systems, especially going forward into the higher performance levels that are required by today's systems. And so what are some of those requirements that we're confronted with? A lot more traffic. There's all kinds of data, video, control, command. The trends in the signals for communications is they're more complicated. They're more channels, that you need higher dynamic range. They need to be secure. They need to be encrypted. You also need reliability. You need to be able to communicate reliably through different radios. You often need diversity strategies, and you often need to mitigate co-site interference. You also find communications on virtually every single military platform, from a troop all the way up to, a very large aircraft carrier, and everything in between. Every one of these different platforms needs to be able to communicate with the other platforms. And there's a lot of applications in terms of signal processing and analysis that goes on in communication systems, where you're trying to classify, identify, decode, monitor, or even record the signals. And then you have the environmental problems, swap, and other difficult situations for temperature, vibration, shock. So all of these requirements are basically driving the different aspects of building a communication system, We mentioned the wider bandwidth and the more channels. This is an evolutionary trend in virtually every single communication system. More traffic, more signals to classify and identify. And they all have wider and increasingly wider bandwidths on each of these channels. So what that means is that you need to have faster data converters, and you need to have more digital signal processing in order to be able to first acquire the signals with the wider bandwidths, and then deal with those high data rates that are coming from the A to D converter to be processed in real time, often with the DSP, which is a great choice. And then finally, the connections between the different parts of your system need to be much faster. You need faster links between the boards in your systems, between your acquisition boxes, perhaps in your processing boxes, and this takes place throughout your entire system. So faster system links are required. One of the things that we've been producing over the last over 10 years now are XMC modules, which is really the very popular industry mezzanine standard. It's compatible with a lot of different open architectures, virtually every form factor. It gives you the ability to couple high-speed A to D and D to A converters on the same board with an FPGA, so you can have very tightly coupled connections and do the real-time signal processing and then deliver the processed data across a very fast system bus like PCI Express, for example. Back in 2009, we introduced our first family of XMCs called Cobalt, which is based on the Vertex 6, and then we evolved to Onyx and then Jade. These are all evolutionary products using the same front ends, but with increasingly higher performance levels in terms of the FPGAs on the boards, moving from Vertex 6 to Vertex 7, and then the Jade is our latest Kintex UltraScale product. You take a look at the evolution of Xilinx FPGAs, starting with the Vertex 4, going up to the Kintex UltraScale. What you'll see is the graph shows you different density packages, roughly the same physical size, with increasingly higher levels of logic cells, going from the Vertex 4 all the way up to the Kintex UltraScale. But secondly, you'll also notice that there are a tremendous increase in the number of digital signal processing elements, the DSP blocks inside, where now the latest Kintex UltraScale is 5520 DSP blocks inside, a tremendous resource for communications and for the complex signal processing that our customer systems need today. We've taken then this range of power in terms of the FPGA densities into the different families going across Vertex 6 to Vertex 7 to UltraScale, looking at, for example, the number of logic cells ranging from a low to a high going across this range in different packages, and then also the number of DSP slices ranging from a low to a high number. What you can see, the result here is that this gives you a factor of 10 in terms of scalability from the lowest to the highest. It allows you to select the right FPGA to handle the task at hand, and it also allows you to minimize lifecycle support because you can migrate between members of the family to give you additional capability. Also, what you'll find is that the Kintex UltraScale has some nice advantages in terms of a lower power reduction and lower cost per cell, significant reductions over the two previous families. So not only can you get more performance, you can also get a better metric. So now let's take a look at one of the modules that we have, which is the 200 megahertz quad 16-bit A to D, D to A converter. This is a very, very popular architecture. It really gives you a complete receiver architecture, and it includes, of course, the high-speed A to Ds coupled directly to the Kintex UltraScale FPGA. We give you digital down converters built into the FPGA. This is an important part of our product offerings, which then include specific IP factory installed in the FPGA to give you digital down converters that are so important to virtually every application. We also have a programmable clock synthesizer built in, so you can program any sampling rate simply by setting the number and then connecting it to an external 10 megahertz reference. We have a large DD4 SD-RAM, and there are versions that cover a wide range of different environmental factors. In terms of performance, we spend a lot of time in packaging our devices in terms of layout for shielding, for isolation, for voltage regulation, and a lot of other mechanical structures that we put in to maintain an extremely high dynamic range. Here we're seeing that we are maintaining the 88 dB dynamic range that's published by the Texas Instruments product sheet for the device that we're using. We're maintaining that product sheet's dynamic range performance, even though we're packing these devices very close together, right next to a FPGA that's switching currents and with supply currents up to 30 amps. Let's take an example of one of the communications challenges that we've resolved, and that is a channelizer. In this case, the example is a GSM receiver. GSM represents the bulk of the cell phone or mobile telecommunications traffic in the world, and there are a lot of organizations that need to monitor those signals. So a channelizer is in a very efficient way of implementing a parallel bank of digital down converters. So after the signal is digitized by an A to D converter, you then need to produce a lot of different channels. And the GSM consists of many, many channels, hundreds of channels. So an efficient way to implement digital down conversion for each is essential to get a compact solution. So the FPGA channelizer that we developed for this GSM application gives you a parallel bank of many, many digital down converters spaced equally at 200 kilohertz spacing, which is much more efficient than implementing that same number of conventional digital down converters. So this results in a product which is available both in Vertex 6 and in UltraScale, which can give you a single FPGA solution to capture every possible GSM signal for monitoring applications. In fact, it includes 1,100 GSM digital receivers in a single FPGA. It has two banks of 175 channels for the lower bands, up and down convert, and then it has another pair of banks, each with 375 channels of digital down converters to handle the high band GSM up and down links. So you have a complete solution in a single FPGA, in a single, actually an XMC module, that then can be put into virtually any form factor. So it's a very efficient way of solving this very challenging problem. We also are finding trends that the new high-speed A to D converters are using a new kind of interface different from the LVDS, which was the traditional interface from data converters to our FPGAs. Now we're using the JESD204B gigabit serial interfaces, which replace those parallel LVDS. And the reasons are that you can use far fewer traces and still, because of the high gigabit serial data rates, get the same or higher gigabytes per second delivered from the data converter into the FPGA. So you can really take advantage then of these interfaces because the FPGAs are now coming out with faster and faster gigabit serial ports that can be directly connected to these new class of FPGAs. And our new JADE products offer several new advantages, and one of them is a range of serial links to support these new JESD204B devices, so we can take advantage of the latest technology and data converters in our XMC product line. In terms of FMC, we have also a different form factor, FMC, different from XMC, that is based also on a mezzanine family. The top two boards you see here are a 3U VPX and a PCI Express carrier with the Virtex 7 FPGA on the carrier. And then we have a range of FMC. These are the modules that attach, the mezzanine cards that attach to these carriers to implement different forms of I/O, different numbers of A to D and D to A converters. And in this case, the I/O, of course, is in a separate module than the FPGA, whereas in the XMC, we had the I/O and the FPGA on a single board level product. So let's take a look first at the upper left product, which is our 5973 3U VPX carrier, which we call our Flexor product carrier for 3U VPX. It, of course, has a central Virtex 7 FPGA, a high pin count FMC side. This is where the mezzanine card is attached. A very fast Gen 3 by 8 interface to the system, PCI Express at 8 gigabytes per second peak rates. We also have a configuration manager called Gate Express that allows you to reconfigure the FPGA across the PCI Express bus without rebooting. We have 4 banks of 1 gigabyte DDR3 SD RAM. We have user I/O pins, both parallel and serial. We support many of the popular standards from Vita. And one of them that's very important and key is the optical interface, which is our Vita 66.4. This gives you a 12 gigabyte per second backplane I/O capability that's very important as the data rates of the new data converters gets higher and higher. This is an example of one of the FMC modules, and it's shown here attached to the carrier that we looked at previously. This particular device has 2 3 gigahertz 14-bit A to D converters with digital down converters. We also have 2 2.8 gigahertz D to A converters. So this gives you a complete transceiver solution that allows you to digitize very, very high frequency signals in and out for a communication solution with 560 megahertz channel bandwidth on each of those channels. It also includes an onboard sample clock frequency synthesizer, as we mentioned earlier. A second product is for people who need more channels. In this case, we have a 4-channel 500 megahertz A to D converter. Each of those channels can handle a 200 megahertz channel bandwidth. We also have 4 channels of 2 gigahertz 16-bit D to A. So now this complete 4-channel transceiver is suitable then for handling communications, receive and transmit for signals with up to 200 megahertz signal bandwidth. We're offering our Flexor products as sets which contain both the FMC carrier as well as the FMC module, but also with IP installed in the FPGA to complement that combination of the carrier with the front end with specific IP intended for things like digital down converters, digital up converters, DMA controllers, and so forth. These are available in 2 different form factors, 3U VPX and PCI Express. We have optical interfaces on both. We'll look at that in just a minute. They're available with standard features like A to Ds and D to As, and also with an enhanced IP that provide digital down converters as well. All completely integrated, completely supported with software development tools and with FPGA development tools using the latest Xilinx development tools and Pentec's latest FPGA design kits. The combination of the Flexor FMC and the carrier, called a Flexor set, really speeds development because it eliminates a lot of the development that customers might have to do if they were to get the 2 separate boards from different vendors. So now you get a full support package, fully installed IP, fully supported software, fully supported FPGA development tools from a single vendor, and that's Pentec. Getting back a little bit to that backplane, the optical backplane that I mentioned before, this is an extremely powerful interface for 3U and or 6U VPX products by giving you an optical connection from the module, which you see here, where this metal housing replaces half of the VPX P2 connector on the module, and there's a mating housing on the a backplane, as you see here. Each of these housings contain what's called an MT optical ferrule. This is a standard connector widely used in the industry that can support virtually any serial protocol that you might need or want to have in your embedded system, such as serial FPDP, Aurora, 10 gigabit Ethernet, and so forth. So the whole idea is that this interface to the backplane gives you connections between modules within the backplane and also connections to other chassis that may be located remotely. The VITA 66.4 standard was ratified this year in May. One of the powerful things you can do with the optical interfaces is, as I mentioned before, to connect boards within a chassis. So here we see two Flexor 3U VPX cards and a chassis connected together through an optical interface. Remember, this can be 12 gigabytes per second, full duplex in each direction. There are also bulkhead connectors available that support the same MT type of connectors that allow you to connect to a remote system, perhaps a remote sensor acquisition system that might be located on the mast of an antenna on a ship, for example. You bring the signals across optically, and it gives you a lot of really nice advantage. Very high data rates. It radiates no EMI, so it's completely immune to eavesdropping. It also is immune to radiation from noisy equipment that might be on the ship or other high-power antennas that might be in the vicinity. So there's no degradation, and the cable is smaller and lighter than copper. Some really nice advantages to a copper-connected system, especially over distances. We've taken a lot of that technology in the board-level products that we just looked at, and we've combined it in our recorder group, which is a separate group within Pentec, to produce an intelligent RF scanning recorder system that can handle bandwidths up to 26 gigahertz, particularly suitable for virtually any communication system. We have a graphical interface on the system, and of course, all of the software radio functions are supported with FPGA technology. We have different versions, laboratory, rugged, and portable versions. It uses our system flow recording real-time architecture, and it's suitable for searching, detection, and recording either in manual or automatic detection modes. So we find that a lot of communication customers use this for testing an RF system for communications to validate their particular system and how well it performs. We have storage capacities of over 200 terabytes in these systems, so they're quite capable. So just as a summary, what we're saying is we have a lot of different solutions for communications, all FPGA-centric. They're COTS products. They're competitively priced, and they're ready to be used in a lot of different environments. We find that the latest FPGAs are one of the only effective ways to give you the horsepower that you need and still maintain the swap factors. We install a lot of DSP functions in the FPGA as it comes from the factory, so it's all ready to use and supported with software. We're now using the new JESD 204B serial interfaces. We're connecting system elements together using PCI Express Gen 3 to eliminate bottlenecks. We're also integrating these components into complete systems that are ready to use as a system. We're taking advantage of the new standards for the optical interfaces that we saw, the VITA 66.4, to gain all of those benefits, especially for remote sensor systems. And of course, lastly, the open architecture standard-based approach to delivering these systems really gives you a very nice new technology insertion and protection against obsolescence. So those are the points I wanted to bring across today. If you have any more questions, you can ask them now, and also go to our website at pentec.com to get information about any of the technology we talked about today. So now I'd like to turn it back to John.
Thank you, Rodger. Excellent presentation by you and Noah. Now let's get right to our Q&A. Got a question here. I'm going to go this one to Noah. Is there any reason to use Stratix versus a Xilinx device? Is one better for some applications than others, or is it more just customer preference? I think you guys offer both. Rodger, do you guys? I don't think that Pentec just is a Xilinx house, if I'm correct. But,
right.
So I guess this one's for Noah.
Yeah, we do offer both Xilinx and Altera. We were originally a Xilinx house. We've been offering Altera for 5 or 6 years now as well. So the answer is debatable, of course. Yeah, some people are a Xilinx or an Altera house from the beginning. Others are agnostic and just looking for the best sort of price performance for their particular application at that time. One of the particular advantages for the Stratix 10 devices that are coming out is in their floating point performance because they have hardcore floating point. So they will be particularly well suited to a floating point type of application. Otherwise, it's usually sort of just a matter of price to amount of resources. That's typically how our customers make a decision.
Okay, thank you. Next question I have is for Rodger. Why not simply use the widest bandwidth ADC and then use FPGA DSPs to extract the signals you want?
We do get that question often, and in fact, when you're doing communication systems, just digitizing everything can often limit the performance of the system, especially if you have a lot of noise or large interfering signals in the bandwidth that you're digitizing. It can limit the dynamic range in the signal range that you really are interested in. So there's a trade-off. Fortunately, we now have the ability to digitize very wide bandwidth signals and choose exactly what portion of that we want to band limit or translate or filter. So it's a benefit, but also it's not a final solution to every problem, where you have to actually consider the strong signal interferers and the noise that might contaminate the performance.
Okay, thank you. Next question. Do FPGA-based solutions for military communications, software-defined radio, essentially perform the same or similar tasks for electronic warfare and radar applications? Are there any differences in requirements? I'll go with Noah, then Rodger, you can chime in too. I know your company plays in this area as well.
Yeah, so FPGA-based solutions, whether they're suitable for SDR as well as electronic warfare and radar applications. Yeah, they often are. There's usually similar sort of front-end processing FPGA requirements. Usually the differences would come in sample rate of the ADCs and DACs, or an EW system may have a minimum latency or a maximum latency requirement from the ADC through the FPGA to the DAC. But there's more and more integration of trying to use the same aperture and have multiple systems from SDR, EW, and radar systems all using that same aperture and using a common set of architecture. So that's becoming more and more possible with open standards and VITA 49 and things like that.
Yeah, I agree with all of that. In fact, we sell about half of our products to radar customers, countermeasure customers, as well as communication. So it's about half and half comms and radars. And we do also install special purpose functions for radar, like complete range gate engines inside of our modules, to make those kinds of transient capture, pulse capture functions very easy to use and implement simply by controlling them, the existing engine and software. The other thing that we do see is we see the bandwidth. Some of the new radars are also very high bandwidth. So that is a trend, and the very low latency, as Noah mentioned, is an extremely important feature that FPGAs can bring, often in a much better way than you can do using a CPU or a GPU. FPGAs can really do an excellent job, especially with some of the products that I spoke about earlier today.
Okay. Thank you, Rodger. Next question from the audience. It seems like the pitch for this talk is that FPGA is a good medium for military chips. What was the alternative before FPGAs? Rodger, I'm going to go to you.
Okay, sure. We basically started out with DSP chips from Texas Instruments. We then migrated over to PowerPCs for doing this kind of work. And then FPGAs, which evolved from programmable logic and PLDs and so forth, started acquiring the benefits of having DSP capabilities. And that capability was kind of the kickoff to having DSPs be usable in the communications and radar functions that we're talking about. That was the critical vector, if you want, that led to the widespread use of FPGAs in communications and radar. And now, of course, as I mentioned, we've got 5,520 DSP blocks inside of our Kintex UltraScale FPGA that are extremely well, ideally suited for doing the kinds of processing that we need in these modern communication systems.
Thank you. And that brings up a question here as well. Do you have any backward compatibility challenges occur when Xilinx or Intel, formerly Altera, of course, release a new product family? I remember backward compatibility being quite important to users of the DSP chips you just mentioned from Texas Instruments and Analog Devices back in the day. Is it a different challenge today, or is it who'd like to take that? That's not for us.
Yeah, I'll take a shot at it. There are always challenges of that nature. What we hope and pray is that when the FPGA from a particular vendor, Xilinx or Altera, is announced, that they will continue to maintain production of that chip for as long as possible. And in fact, generally in the industry, that has been done. So we're enjoying the ability to perhaps deliver products over a 10 or even 15-year period of time because of the production that's going on by the vendor. And we do have life cycle management programs that allow us to purchase a certain quantity before the part goes end of life to maintain or guarantee production going forward, even after an end of life event.
Noah, can you add anything to that about what you guys see from a backward compatibility with that? FPGAs.
I think Rodger covered it pretty well. Yeah.
Okay. Next question for the audience for Noah. What are the top 2 challenges in design and verification of the FPGA designs? What phases take the most time or other resources?
So I'd say what we see from our customers, challenges often come in. So keep in mind, we and our customers are often concerned not just with sort of a single FPGA design, but it's multiple FPGAs integrating with converters, integrating with maybe SBCs on a back end in a large system. And so one of the major challenges is getting multiple FPGA designs all running at the same time, integrated into a system. And another challenge is probably just the simulation time and development of the HDL in order to ensure that the application is going to run properly. And sort of both of those challenges is why we came up with the Open Project Builder development environment, and also our ecosystem of products where we have FPGA boards, mezzanine cards, backplanes, Ethernet switches, all of those things integrated in an environment that we know will work. So the Open Project Builder, what it provides is the ability to very quickly get not only your board support cores, but also your algorithmic and data flow cores in one environment and run them on hardware in a matter of hours instead of days or weeks. So you can very quickly get to hardware in the loop type of bugging and application work. And then since it's sort of a system-level design tool, that also integrates with our ecosystem of products and being able to integrate that whole system, not just thinking about, this one FPGA is what's most important to me, and I just have to get that one FPGA working. It's really about getting the whole system working.
Okay, thank you. Next question for Rodger. What wavelength optical links are you using and why?
Currently, we're using 850 nanometer, which is the multimode fiber length, simply because the products that are available, the transceiver products that are available now, operate at that rate, which gives you a peak rate of about 14 gigabits or gigabaud on the optical links. We are expecting a transition over to single mode transceivers, in which case we'll be able to go over much longer distances and perhaps even at higher data rates, going up towards the 20, 28 gigabaud range. So the technology is moving all the time, but the basic specification for the VITA standards that cover the optical interfaces will support that evolving speed and different wavelengths. So we're really covered with the standard.
Okay, thank you. Next question for Noah. Can I import other HDL into your application programming tool?
Yes. Other HDL from VHDL or a high-level synthesis output or Verilog, any HDL can be imported in. So if you have something that's been government certified or something like that where you can't change that code, then that can be imported and used.
Okay. Next question. Speaking of development, can OpenCL be used for development of programming the FPGA? I would like to take that. Noah?
Yeah, sure. I could take that. OpenCL can be used in some cases. So we found some customers who are sort of thinking of migrating from the GPU environment would like to use OpenCL. We've also found that the high-level synthesis is a very useful way of doing that migration. One of the advantages of that is that you can still use sort of the other board support level cores that are already developed, and while still bringing in high-level synthesis tools.
I'd like to just add to echo what Noah said, and also to add that the new graphical design methodology for FPGA development is it's much more productive in terms of getting a design out and tested and then supported and maintained. The other thing that we are promoting is the AXI4 interfaces on the FPGA IP blocks, which is now more of a standard within the Xilinx community of producing and offering IP that's extremely flexible and connectable within their graphical design tool in Vivado to allow you to create new designs, modify designs, and do your testing and development in a much more efficient way. This is supported in our new Navigator design suite, which we just released a few weeks ago.
Okay. Next question for Rodger. Aren't ASIC digital down converters less expensive and lower power than FPGA DDCs?
Yes. In fact, we used to use ASIC digital down converters when we didn't have the ability to do so in FPGAs. So the problem is that they do one thing, and they only have one certain limited range of functions and parameters. With FPGAs, what you can do is you can then take a wide range of different operating conditions, implement them in the FPGA to have them be much more flexible than the traditional ASIC digital down converters.
Okay. Next question for Noah. Will the FPGA processing board Zinc 7's SoC be upgraded to UltraScale?
Yes. So we're working on upgrading that Zinc SoC to be a Zinc, an UltraScale plus Zinc SoC. which has some additional features that some customers, some programs require.
Okay. Time for 2 more questions. Noah, how do you make an optical connection to your UltraScale 3U card?
So that's done using our 24x optical mezzanine card. So it has 24 bidirectional connections that are provided through our Wild FMC Plus interface to the FPGA. Those connections in the OpenVPX world, they can either be on the front panel or they can be routed to a Vita 66 connector on the back plane. They run at 14 gigabit line rate today per connection and 28 gigabit in the next few months.
Excellent. Well, that brings us right to our time limit for today. Sorry we could not get to all of your questions. Someone may get back to you after the ECAST with more information. I'd like to thank Noah Donaldson and Rodger Hosking for speaking today, and Annapolis Microsystems and Pentec for sponsoring today's event. Just a reminder that this and all OpenSystems Media ECAST are copyrighted and may not be recorded or used in any way without the express written consent of OpenSystems Media. This ECAST will be archived online today and be available for 1 year. There will also be an MP3 version of the event available. Thank you all for attending, and I look forward to seeing you on future OpenSystems Media ECAST. Goodbye.